So let's do another little case study. So this is a routing table. And what a routing table is a way to map where you want to go. You have some information that wants to go somewhere. How do you get it to that destination? And this is actually a very dumb routing table. So for instance, here, uh-oh, did I break it? So right here, you see that the destination is 0.0.0.0. It's on my home network. There's only one way to the internet. So it would actually go to my router. Now, in a real routing table, for like a peer, you'll have multiple instances. So you could say, for instance, all the European IPs, they'll route through this carrier versus all the Russian IPs will go through this carrier and whatnot. And you can have different metrics on it. So this guy here shows the weight of it. So if 10.10.10.1 is down, so my metric 10, it will fall back to the next metric and whatnot. And there's another cool thing where you can actually start trace routing. So to see how data gets from your location to the remote server. So I thought, let's see where the Democratic People's Republic of North Korea server is. And I'm probably on FBI watch list for this, but so I did a trace route from my home in West Campus, Apogee. And you can see that once we hit the core backbone, we stay on Cognitive's network until we hit somewhere in Europe. So I did it from ComSoc. And you see that UT actually stays on level 3 and until we hit Europe. And I did it from, from Canada, from my server up in Canada. And you see that it has even a more direct connection to wherever this Democratic People's Republic of Korea website is hosted. So here's a pretty graph. You can see that back coming from Austin, it took 2 different routes, one through Dallas, one through Houston. They both went through Atlanta. Atlanta's a big hub for communications. And they jumped up to Washington, D.C. Level 3 decided to leave on an underground cable from Washington, D.C. back to London. And actually, one of the times I ran this, it actually went back to New York to go back to the UK. But that's the internet. The other one went through New York, and then it went to Liverpool, and then to the Netherlands. So from this little graph, you can kind of deduce that North Korea's website is in the Netherlands, which makes sense because they have a lot of open hosting. But anyways, so who actually manages the internet? I mean, someone has to come up with protocols. Someone has to give out IP addresses. If you own an IP or a domain, you expect to own that, right? So there has to be a body that actually understands that fact and keeps that the way it is. So the big one is ICANN. I can't find a better logo. This is the best logo from like the 1990s. But they're the Internet Assigned Numbers Authority, and they give out IP addresses. But the thing is, they don't actually do any of the work. They have different registrars, one in North America, one for Europe, one for Asia, one for Latin America, and one for Africa. That actually does all the work needed to actually make the internet work. So basically, you got ICANN at the top with a bunch of IP addresses, the root hint for DNS and whatnot. And you got all your different registrars there. ICANN will give out those IP addresses, and then the people go like, we want IP addresses. And then the local registrars will go ahead and give out those IP addresses. The thing that's happening now with IPv4 is we're running out of IPv4s. So what happens when the local registrars don't have any more internet addresses? And the answer, anybody know? Anybody know? Wrong. IPv6.
No. You ask for more from other people.
You steal from your.
So anybody know what will happen when we actually run out of IPv4 addresses? In some ways. What will happen is, just like any other natural resource, a bidding war will happen, and people could start paying lots of money for an IPv4 address. You saw companies like Microsoft buy companies. I think there was one company that bought Nortel Networks just so they could get their like /16 or something like that. insane. But anyways, so
By the way, UT has 4/16.
really,
Yeah.
well,
And they only use what, 2 of them?
they only
No,
use
we
like,
all of them.
right. Well, anyways,
And started natting all the Wi-Fi?
Yeah, I don't get it.
so IPv6 is a very important technology that needs to happen. Unfortunately, it's not happening as fast as they predicted back in 1994, I think, back in the 90s when the protocol was first designed and approved. So there's this transition technology which would help the transaction. So basically, you would, instead of doing all this dual stack where you have IPv6 to IPv4 tunnels and IPv4 tunnels to IPv6 tunnels, you just go ahead and say this address, IPv6, so the first 32 bits or the first 64 bits of one address is going to be the block of IPv4 networks. And if you want to access the IPv4 internet, you go to this address, append it with the translation version of the IPv4 address. And the problem with this is now you have, when you go through that routing gateway, you become anonymous because you're losing information. So you can now start doing bad things on the internet anonymously, which is bad.
No, that's good.
No, that's bad. So there's another idea called IPv6 rapid development. So basically, this idea is you have an IPv6 only network that wants to access both the IPv4 and IPv6 network. And so you have both networks, except one is in this like weird emulation / transition mode. So you can go through this 6RD gateway and access the IPv6 network while being routed over an IPv4 network. This technology, there's about a 5-page description of just that explains what it does, and it's kind of insane. But anyways, are there any questions about how the internet works? No? Did I explain everything?
So V6 is, or V4 is more desirable because you get a larger amount of addresses in a...
No, so IPv4, the problem with that is it's a 32-bit address.
Mhm.
So that means there's only 2 to the 32 possible addresses you could ever have. And we've run out of allocation of that. We might actually only be using maybe 10% of the addresses. Only 10% of the addresses actually have computers behind of it. But we've allocated 100% at the international registrar. So now the national registries are being very stringent about handing out IPv4 addresses. IPv6 is a 128-bit address, right? 64 bits are public, the other 64 bits are private. So you can get a /64 address, and you still have 2 to the 64, right?
Why would you need that many private addresses?
I don't know. But it fundamentally changes the way the routing and whatnot works almost exactly the same way, but you don't have the concept of a NAT anymore. Because your NAT, your address, is the first 64 bits. And then everything beyond that is your private computers. And the idea is we're moving into an age of the Internet of Things. So like right now I have, let's see here, 1, 2, 3, 4, 5 IP addressable devices on me. Going into the future, we might have hundreds. And in a household, we might have thousands. So that's the idea of what the IPv6 is trying to solve. The problem is like networks aren't designed for it yet. Firewalls, still not designed for it. Firewalls, training, people still prefer IPv4 because it's easier.
My light bulbs have IP addresses.
Yay. Any other questions? Cool? Savvy? Cool. Well, thank you.